Hi, good afternoon, everyone. It's great to have you here. My name is Anaís Gomez from Siman in Mexico. Today, I will present our work tuning laser-induced graphene electrode properties for pH detection in wearable devices. For introduction, laser-induced graphene or LIG is a carbon material made directly of polyimide using carbon dioxide laser light. By changing two parameters, such as laser power and scan speed, we control how much heat is applied. This heat changes the material from amorphous carbon to the graphene carbons. These parameters affect the surface structure, the fiber arrangement, pore size, conductivity, and even how the surface interacts with liquids. Studies have shown that modifying these surface properties change how electrical charge moves, which is a key to electrochemical sensors. Here we focus on pH sensing and examples, because pH is an important indicator for health monitoring, especially for human fluids. Unlike reading glass pH electrodes, LIG is flexible, can be worn on skin and does not need extra current. In this work, we fabricate LIG electrodes with different laser settings and analyze the morphology, structure, and surface affinity to liquids to evaluate the performance for pH detection. Okay, let's continue with the methodology. First, we select different combinations of laser power and scan speed to explore a wide range in the condition in the table 1. Next, we engrave the polyimide surface using carbon dioxide laser, forming the light directly on the substrate. Then, silver ink was deposited to generate the electric contact, and the passivation process was carried out. After that, the surface morphology was mapped, ranking from marked porous to marked fibrous structures to determine which adhere to the polyimide substrate. In this case, the blue configuration shows poor adhesion, whereas the green ones adhere successfully. The structure with higher fiber content reference to high will predominantly located in the orange in the red regions. Then, we characterize the samples in set of the morphology Raman technique to evaluate the effects in the carbon structure and contact angle measured for surface affinity to liquids. Finally, for the pH detection, we use an open circuit imputation septum. Our LIGS electrode was the working electrode, and we connect the commercial reference electrode. We test in the standard buffer solution for pH 4, 7, and 10, always following the same routine. First, we place the electrode in the solution, stay for 5 seconds, and then rest for 15 seconds and cool stabilize. After that, we record the open circuit potential for 20 seconds. Once finished, we rinse the electrodes 3 times before moving to the next pH. We repeat the process on 3 full cycles. Okay, in this case, in the results. The figure 2 illustrates how the pH buffer doublet interact with the active light area. To evaluate the behavior, contact angle measurements will conduct allow the distinction between the more fibrous and less fibrous surface. The figure 2b shows two representative examples, a more fibrous and less fibrous. The full analysis for the 5 configuration, the figure 2c and 2d, reveals all represent a contact angle above 90 degrees, indicate hydrophobic behavior within a similar trend observed in the droplet base width. This result suggests that morphology plays a key role in the surface ability to repel or retain liquids. Now, moving in the Raman result, in the figure 3, again, the results come from the set of 5 leaks configurations. And here we show in the figure GA one sample spectrum. The 25500 configuration presents clear D, G, and 2B bands. The AD over an AG ratio is about 1.75, which tells us about the phase density and degree of the gravitation. In this case, the relation A to D over AG ratio is about 1.46 consist with the fuel layer graphene. These characteristics are important because they relate to the material conductivity and sensing performance. In the figure 4, same images are present to two select configurations, 70305 and 25500. Rebel difference in fiber density only as an example to illustrate the morphology. The image reveals difference in the fiber density and porosity depend on the laser parameters, from less fibrous surface to highly porous and fiber-rich networks. This morphology variation can directly affect the surface area and result the charge transfer during the electrochemical sensing. Finally, pH detection was evaluated for all configurations that adhere to substrate. In the figure A, the R-squared values are shown, with the best performance obtained the 25% power and 500 milliseconds. For leak samples per configuration were used to ensure repeatability. For this configuration, the linear was very high. R-squared is 0.99 and slope was 20.95 millivolts per pH, represent the sensitivity. The average repeatability rotation was 96.3%, meaning the sensor maintained almost the same potential value of the same pH in repeat measurements, even without compositing coating. Hysteresis was calculated, and the potential difference for pH 4 between the beginning and the end in the measurement cycle. This value is shown wherever the sensor response shifts after several pH changes. Work conclusion. In this work, different leak configurations were evaluated to establish the relationship between fabrication parameters in the material morphology, structure, and surface properties, aiming to optimize the performance pH detection. SEM analyzed rebel porous interconnect fiber networks. Raman spectroscopy confirming the presence of the nanocrystalline carbon, and contact angle measurement indicate hydrophobic surface. We were able to detect pH from 4 to the 10 without any additional coatings. The main result for the 25% power and 500 millimeters per second laser setting, which got high sensitivity, excellent linear. This shows that the laser power and speed during fabrication are key to making the sensor work effectively and ready for feedback step toward building stable, reliable leak-based pH sensor that can be adapted for more advanced application in the future. Finally, I think thus the contributed the measurement of Dr. Pedro Pisa, Dr. Mónica Mendoza, Mr. Ensaiz Carla Campos, and the Estancias Postdoctorales for Mexico program, and the support for sharing this QR code or reference. Thank you so much for taking the time to listen to my presentation, and if you have any question, I will be happy to answer them.